we're going to discuss how derivatives affect the shapes of graphs. Now, initially, we're talking about if the derivative is greater than 0. Remember what that would mean. That would mean that the slope is greater than 0. Can you draw something in the air with your finger where the slope is greater than 0? And you probably drew something that went like this. And you're right. So if the derivative is greater than 0, then the function that we're talking about, f of x, is increasing. And that is a key concept, a key vocabulary term here, increasing. And the criteria that causes us to know that a function is increasing. The derivative is greater than 0, the function is increasing. What if the derivative, what if the slope was less than 0? Well, if you think about that, if you draw that in the air, we need a slope less than 0. It's going to go like that. And that would mean, going to lead us to another vocabulary term here. That means that the function, f of x, is decreasing. So if we find a derivative, and we make a sign chart for it, we're going to be able to figure out when the function is increasing and when the function is decreasing, without actually having a graph on our calculator. Now, the first derivative test for max and min. We've got some nice continuous function. And it's got a critical number at c. That means, again, remember the derivative is 0 or the derivative doesn't exist. If the slope, if f primed of x, changes from positive to negative, let's draw a picture of that. Let's draw the slope being positive and then the slope changing to being negative. Well, when that happened, what did you have? And this is called the first derivative test for max and min. If the derivative changes from positive to negative at c, then f of x has a local, a local max. At x equals c. And that would make sense when we think about slope changing from positive to negative, something going up turning into something coming down. Or in part B, the slope, the derivative changes from being negative, so we are decreasing, to positive, which means we are increasing. Yeah, where that takes place, at that critical number of c, where the slope is 0. Slope is 0 here. Slope is 0 here. Where that slope is 0, where that change takes place, f of x has a local minimum. So that's how we're going to explain how we find maximums and minimums without a calculator. We're going to find those critical numbers and we're going to test using sign charts whether the derivative is positive or negative leading up to those critical values. Concavity test. If the second derivative is positive, okay, now I'm just going to write this over here. If derivative of derivative greater than 0, derivative greater than 0. Second derivative greater than 0, or derivative of the derivative is greater than 0. Anytime the derivative is greater than 0, I'm going to say that the function is increasing. And I can replace derivative with the word slope. So the slope is increasing. The slope is getting bigger and bigger and bigger. And if the slope is getting bigger and bigger and bigger, I might have a situation that looks like this. Slope is getting bigger and bigger and bigger. I might also have a situation that looks like this, where the slope starts out to be very negative, but then becomes bigger and bigger and bigger. The slope was negative, but now it's getting pretty darn close to 0. Anything along what I've just drawn here is where the slope is getting bigger, where the derivative of the derivative is greater than 0, where the second derivative is greater than 0. Then the original function f of x is, we're going to look at this picture that we've drawn over here. And the term that we're going to use, and the vocabulary term that you're going to need to know, is f of x is concave up is when the function is shaped like a cup. That's the handle of the cup I just put in there. It's pretty good, isn't it? What about when the second derivative is negative? That means, again, the derivative of the derivative is less than 0. When the derivative is less than 0, that means we're decreasing. Learned that on the previous slide. And I'll replace this word, derivative, with slope. And so the slope is decreasing. The slope is getting smaller and smaller and smaller. What does that look like? Well, let's start out with a big slope. And let's have it get smaller and smaller and smaller. And it eventually can become 0. And then it's going to become smaller, which means it's becoming negative and more negative and more negative. That's what this situation looks like. When the second derivative is less than 0, then the original function is f of x. And another vocabulary term here, this is concave. This would be considered concave down when the second derivative is less than 0. Okay. Now, let's say f of x is some continuous function. And at some mythical value of c, the second derivative changes sign. So I'm going to draw a graph. I'm going to draw something that kind of looks like the sine function. Okay. No. F of x is continuous. Yep. It sure looks like it. And at some point c, the second derivative changes sign. Well, it looks like the second derivative here looks like we are concave down, concave down, concave down, which means the second derivative is negative. But then we get to a certain point where it looks like we're shaped like a cup. We're concave up, concave up, concave up, concave up, concave up. Until we get to a certain point, and then it looks again like somewhere in there, this changes to being concave down, and we're no longer shaped like a cup. We're actually shaped like a frown. Concave down, shaped like a frown. Well, okay. There's that magical value of C, where concave down turns into concave up, or when concave up turns into concave down. If we've got a continuous function and the second derivative changes sign at C, then the point C, and whatever the y value is called a point of inflection. Another vocabulary term. All right, so point of inflection is where the second derivative changes from, well, it looks like the second derivative was negative and now it changed to positive, or where the second derivative changes from being positive to being negative. We have to be specific about what the sign started out as and what it changed to. Then we have something called the second derivative test. Man, there's a lot of information in this section. This is going to take a little time to process. The second derivative test for max and min. Derivative is zero. That means the slope is zero. But the second derivative is positive. So derivative is zero. That means we've got a horizontal tangent. And the second derivative is positive. Concave up. Okay, let's draw that situation. Let's draw concave up. And let's have a place where the derivative was zero. What is that point? When you're concave up, but you have a slope of zero, that makes the point then C, f of C, is a, what are you going to call it? And hopefully you're going to agree with me. Call it a minimum. When the first derivative is zero and the second derivative is positive. If you draw the picture, what about when the slope is zero and the second derivative is negative? That means concave down. Let's draw concave down. Let's have a place where the slope is zero, and when that happens, what are you going to call that point? Well, by this thing called the second derivative test. Then the point C, f of C, is a maximum. And I really think that memorizing these two situations is kind of difficult. So I always rely on drawing a picture, and then it becomes very obvious whether I'm talking about a maximum or a minimum. Now, the next two slides have examples. Finding all 7 of these: increase, decrease, max, min, concave up, concave down, points of inflection. Then sketch the graph. You know what? AP doesn't get all hung up on you sketching the graph. I'm not going to either. But they do get hung up on you finding these intervals of increase, decrease, max, min, intervals of concave up, intervals of concave down, points of inflection. So let's focus our attention on those things. And we're only going to do this one example. We won't do the one on the next slide. Okay. First derivative. If we want to know anything about increase, decrease, max, min, we're going to use first derivative, and f prime of x is equal to 4x cubed minus 12x. And I am interested in finding the critical values, so I'm setting that equal to 0. So x squared straight up. Now, to find out where this is equal to 0, I think I'm going to factor out 4x squared. And I'm going to multiply that by x minus 3. And this is going to be equal to 0. Now, I know this is equal to 0 at x equals 0, and hopefully you're saying, oops, hopefully you're saying to yourself x equals 3. All right. So let's draw a sign chart. And let's put only the critical values of 0 and 3 on here. Now, I want to see what's going on in this interval, and this interval. So I'm going to check any number, first of all, less than 0. Maybe I'll mentally think of a -1. If I put a -1 in here and a -1 in here, am I going to get a positive result or a negative? If I put a -1 in here, I'll get a positive result. And a -1 in here is going to give me a negative inside the parentheses. And positive times a negative is negative. What if I choose something between 0 and 3? If I choose something like 2. Well, this is going to be positive, and this is still going to be negative. And what about at, oh, something bigger than 3, something like 4? Well, it looks like this will be positive, and this will be positive. And so finally, my first derivative will be positive. So I want to know the intervals of increase. I think we are increasing wherever first derivative is positive. I think that starts at 3. It goes all the way to infinity. And I'm wondering, where does this function decrease? And I'm thinking that that starts at negative infinity and goes until 0, and then just the other side of 0, all the way up to 3. That's where the derivative is negative. Now, to be honest with you, James and the AP exam, they might say that the interval goes from negative infinity to 3. I don't agree with it. I think it's 0. The derivative is 0. I don't think it's positive, nor is it negative. But you may see that, and if you do, don't be surprised. That is apparently acceptable. I just have a problem with it. All right, now let's finish this up. Let's talk about max. Where is there a max? If I ask you at what x value does a maximum occur, you would say there is none. If I would say, would you please explain that to me, you would say, that f primed of x, the derivative, never changes positive to negative. You're very specific about those signs. If I asked you, where is there a local min? At what x value is a local min? You would probably say at x equals 3. If I said, will you explain that to me? You would say that the derivative, f primed of x, changes, and you have to be very specific again, from negative to positive. People will say, oh, the slope changes from negative to positive. Well, yeah, the derivative, slope, those mean the same thing. So that's another way you could say it. I prefer to say derivative changes from negative to positive. Saying the word slope instead of derivative is acceptable. All right. We've done it, we've done it, we've done it, and we've done it. But if we want to know something about concave up, concave down, points of inflection, those are all dependent upon the second derivative. So let's start talking about the second derivative. Here's my derivative up here. So the second derivative, f double prime of x, is going to be equal to 12x squared minus 24x. I'm interested in finding the critical values of that, so I'm going to set that equal to 0. And again, I'll probably factor out a 12x times x minus 2. I want that to equal 0. And I know that that is equal to 0 at x equals 0 and at x is equal to 2. You know, which is kind of interesting because back here, we had a critical value of 0, but it wasn't a max, nor was it a min. Maybe we'll find more out about that as we talk about the second derivative. Well, I'm going to make a sign chart for the second derivative. And I'll put my critical values of 0 and 2 on there. And I want to see what's going on in each of these 3 intervals. So I'm going to start by choosing a negative number, something in here. If I choose any negative number, like a -1, this factor is negative, this factor is negative. When I multiply them, I get positive. What if I choose something in this interval right here? If I choose something like a 1, well, this is positive, and this is negative, and a positive times a negative is negative. What if I'm checking this interval right here? Anything greater than 2. Anything greater than 2, and this is positive. This is positive, so I get a positive result. And those are the signs of the second derivative. So where are we concave up? Well, we got to give an interval where the second derivative is positive. I think I'd start at -infinity and I'd go to 0. I think I'd start at 2 and go to infinity. And what about concave down? I'd want to look at my sign chart and see where my second derivative is negative. And what about points of inflection? You know, if I just asked for the x value, inflection. If I ask for the x value, just give me the x value. asked for the actual point of inflection, you would say, well, it looks like one is happening here at x is 0. And when x is 0, coming back up here to our original function, it looks like y would be 0. I might be asked to explain why. I'd say because the second derivative, f double prime, changes. And I have to be specific. Positive to negative. And it looks like another change in concavity happens, another point of inflection happens when x is 2. Now, when I put a 2 in here in this original function, I think I get 16 minus 32. I think I get negative 16. So if I'm asked for the point, I'm going to get a point. It all depends on what you're asked for. Be conscious of what you're being asked for. I'm asked for an explanation because the second derivative, I've got a point of inflection at 2, negative 16, because the second derivative changes. And I can't just say it changes sign. I have to be specific. It changes from negative to positive. And those are the types of things, those 7 things. Concave up, concave down, points of inflection, increase, decrease, max and min. Those are the types of things you're going to be working on as part of your homework tonight.